Hi everyone, so in this video we discuss subtopic 4.6, which is about torque on coil. I think by now you guys are familiar with the word torque, where we learned this previous semester, in the first semester in chapter 8. Okay, so here in this example, in this topic, what you guys will learn is that you have a force acting on an object. That force is due to the magnetic field and will produce a force that tries to rotate the object. As a result, we call that one as a torque. Okay, in this example, we have a rectangular loop. Okay, I label with P, Q, R, and S, and then you have a uniform magnetic field. Okay, and from previous subtopic, you know that if you have a current carrying conductor sitting in a uniform magnetic field, it will experience a force. Okay, so in this case, can try to look at these four segments separately, okay, and then we discuss about the direction of force, right? So if there's a current flowing in this direction like this, okay, and then we want to determine the direction of force for each segment, like let's say if we try to determine at segment P there, sorry, PS, okay, you have a current going downwards and then you have a magnetic field to the right, so you will have a force going out of the page, right? And then over here you have a force going into the page. This is the direction of your thumb. This is the direction of the magnetic field. Okay, so your force over here will be into the page. Okay, so you have one part, you have force going out on the page. Another part is where the force is going into the page. That force creates a rotational motion. How about the PQ and RS? Okay, for these two, there's no force acting on it because for this part, the magnetic field is actually parallel with the current. So if it is parallel and you want to use the formula of force, you have a sine theta which is equals to sine 0. That one will produce a 0 force. So this part basically produce no force. Okay, so if I try to do a side view, so this is the top view, we are looking from the top. What if we are looking from this side? Okay, maybe I can label this one as RS, right? So you can see that this one is the current that is going into the page. I mean, if we flip it, right, this is going into the page. Like this is the actual triangle just now. So the current direction here is into the page, while this one is going out of the page. That's why I label out like that and in. So this is the symbol that represent the direction of current, I. Okay, magnetic field still going to the right. Okay, we want to determine the direction of force. We determined just now, just that I want to confirm it one more time. So in this case, your thumb will be pointing out of the page. This will be the direction of your fingers, right, following the direction of the magnetic field. So this will be your palm, right? This will be your direction of force, which is going upwards. Okay, so the force over here is going upwards, and over here you have a force going, okay, it should be going downwards, but you just show it one more time. Direction of the thumb is going into the page, following the direction of current, and then this would be your fingers, which is following the direction of magnetic field, and the force is going, sorry, I think I imagine, okay, so the current is going into the page, so the thumb is going into the page, so this would be your four fingers, right? So your fingers, this is your hand, so your palm will be in that direction, so force is downwards. Okay, because you have a two force that is going going up and down, then if this is the axis of the rotation over here, okay, this is a like a fixed point, so you can see that this one will be going up and down, so this one will create a rotational motion. Okay, Okay, so if you guys still remember, previous semester you learn about torque, where torque is equals to RF sine theta. Okay, and just taking the direction of force, I'll just put it over here. Okay, so if I want to calculate net torque, okay, I can do torque is equals to torque 1 plus torque 2. Let's say if I label this one as F1 and F2, basically the magnitudes are the same, right? So then I will have RF sine theta plus RF sine theta. Okay, if the distance or the length between R and S is B, that means my R, so basically R is the distance between the force and the center of rotation. So this would be the length of your R. Since this one is B, the total length is B, half of that would be B over 2. So B over 2 F sine theta plus B over 2 F sine theta. Now I can substitute the equation for force. Okay, you know that force for a long conducting wire, straight wire, force is equals to BIL sine theta. Okay, so if I substitute BIL, so it will be magnetic field B, and then the current I, and then the length L, but in this case your length is equals to A okay, and then you still have B over 2 there, plus B over 2 BIA sine theta. Okay, since the currents are the same on those two parts, so everything is the same now, I can factorize the BIA, okay, sine theta, and then B over 2 plus B over 2 is equals to B. And then since A multiplied by B is equals to the area, so it's the area, right? So I can simplify this further. This one becomes BI area sine theta. Okay, and this is how you want to calculate the torque on the coil. And if I have more than one turns, so my equation can torque equals to NIAB sine theta. Okay, and here represent numbers of turn. So if I have a rectangular coil with one turn, then this one becomes 1. The theta there represent the angle between B magnetic field and A normal. I put A normal, it means that the normal to the plane of the coil. That means if you have a surface like your table there, normal to that is going perpendicularly upwards to your table. Okay, so you have to determine the direction of B and A, and then that will be the angle here. Okay, be careful with this one, so you have to be careful a little bit. Okay, so basically this is the main equation you want to calculate torque. Okay, and torque is basically RF, so the unit will be meter and Newton. So meter Newton. Okay, one of the application of this one that you have to know is about galvanometer. So you know that the difference between galvanometers and ammeter, right? So here you can see that the zero scale here is actually in the middle. Okay, So if there's no current, basically the needle will stay in the center here. Okay, in this case you have an something that looks like a circular magnet. Okay, the reason why you have a circular magnet so that it can produce a magnetic field like that. So the magnetic field will be, it will look radial to the coil here. Okay, so you have a coil. Okay, imagine that it is being turns like that, right? And you have a spring. Okay, this is like a circular spring where we try to produce a force in opposite direction to the motion of the needle. Okay, so you can see that it is written here, magnetic surface is curved. This ensure the force is constant. Magnetic force for the curved magnet is perpendicular to the magnet surface, and restoring spring returns with the spring loaded pointer to 0 when there's no current flow. Reversing the current reverses the direction of the pointer. Okay, so the segments that that has a force, that produce a force, is actually this part. Okay, so in example, if I have a current that is going in that direction, that means over here it's going up or out of the page. So that one is into the page, right? So if I use palm rule, okay, magnetic field in that direction, B, fingers in that direction, thumb is going out of the page, so the force it produced will be in that direction. Okay, and then in this example, thumb going into the page, and then magnetic field in that direction. This is the B magnetic field, fingers, right? So my palm will be in this direction, force in that direction. So you have force here, force there. So we try to rotate towards this part over here. Okay, obviously this one is the opposite lah. So if you reverse the current, then you have something like that. Okay, I think you can imagine how it works. Okay, if we try to look at one of the examples, here you have a circular loop carrying a current of 2 ampere. So previously when I tried to show you how to derive, okay, we derive it assuming that it's actually a rectangular coil. But if you use those formula, the area now becomes the circular area lah. Okay, it says that the current is 2 ampere and radius 10 cm. It's placed in a magnetic field of 0.5 Tesla. Calculate the torque acting on the loop when it's placed perpendicular to the field or the parallel to the field. So you have one cases where the plane is perpendicular, another one is parallel. Okay, first thing first, we take out the information first. So I just want to write over there, so I bring it down here. Okay, it says that the current I is equals to 2 ampere. Okay, magnetic field B is equals to 0.5 Tesla. The radius is equals to 10 centimeter, 0.1. And you know that since this one is circular loop, so A is equals to pi r square. And then a circular loop means that numbers of loop is equals to 1. Okay, so basically we want to apply equation of torque equals to NIAB sine theta. The key thing here is you have to identify the angle first. Okay, so remember that the angle is actually 90 degrees to the surface. So this is your surface. You can imagine that this is a circle, right? But this is a side view. Okay, I draw this one like it has a multiple loop. Okay, but in this question it only have one loop, so satu je lah, like this. Okay, I just draw it like this. Okay, the area is 90 degrees or normal to the surface, so area will be in this direction. Okay, so let's say if I try to draw this one inside the magnetic field there. Okay, for when the plane is perpendicular to the field, what does it mean is that the plane is actually sitting like this. So the plane itself is perpendicular to the field. So this is the plane, right? It is a perpendicular to the field. Okay, remember this. On the other hand, on the right hand side, you have parallel to the field. So it looks something like this. Okay, magnetic field is parallel to the plane. So the plane is in this direction, magnetic field in that direction. So parallel. Okay. Okay, now the angle here for part A, question A, when it is perpendicular to the field. So this is your A is to the right, your B is to the right, so the angle theta will be equals to 0 degree. Okay, on the other hand, on part B, you have area that is going upwards, B to the right, so theta is equals to 90 degrees. Okay, so you want to apply the same formula, torque equals to NIAB sine theta okay, the only difference will be the angle. So N equals to 1, I equals to 2, A equals to pi r square, pi 0.1 square, B is equals to 0.5. On this part A, sine theta is equals to sine 0. So this part becomes 0, the whole thing becomes 0. Okay. For this one, torque equals to 1, current equals to 2, area equals to pi r square, and then multiply by magnetic field. This one becomes sine 90 degrees. Okay, just have to drag this one a little bit to the left. You know that sine 90 is equals to 1. As a result, if you calculate, you should get 0.031. The unit will be Newton meter. Okay, that's it for this video.